All right, hi everyone. Welcome to the Amaldi session 11-1. This is one of the parallel sessions we have this morning or afternoon or wherever you are in the world. So this is the session on techniques and parameter estimation, and the chair of the session is Francesco Panarale. So I will turn over to Francesco right now. Go ahead.
Thank you very much, Scott. Yeah, welcome indeed to this session on parameter estimation. I wanted to remind you that we follow the APS meetings code of conduct and that the speakers have 15 minutes for their presentations, followed by 5 minutes of a question and answer session. And our first speaker today is Barry Ginat. I hope I'm not mispronouncing surnames and names today. Apologies in advance for this. And the talk is titled Probability Distribution of Astrophysical Gravitational Wave Background Fluctuations. So take it away, Barry.
Thank you very much. I'm Barry Ginat, PhD student at Technion in Israel, and I'll talk to you about the gravitational wave background. So the gravitational wave background is basically the sum of all gravitational waves that arrive here at Earth at a given moment in time. And most of them are very weak, so we can't detect them as individual events, and that's why they're called the gravitational wave background. Now, I'll be talking mostly about the frequencies where this background is composed mostly of compact binaries, so stellar mass binaries like LIGO sources, LVK sources. We have the recent result from the nanograph collaboration about supermassive black hole detection. I'm not going to talk about that much today. So the goal of this talk is to describe a way to calculate the statistical properties of such a gravitational wave background. And I'll do it by calculating the full probability distribution of the strain amplitude. So how do you go about that? Well, you take all the gravitational waves that are arriving at the detector, and you draw them as complex numbers in the complex plane. So you start with the first one, and then you add the second one, and third one, and fourth one, and so on, until you've added all of them. And the strain amplitude that the detector is going to measure is the position of this let's say walker doing a random walk on the plane. Now it's a random walk because each of these gravitational wave strains is essentially a random complex number, because the properties of the gravitational wave sources are drawn from some random distribution. I'm going to assume that every gravitational wave source is drawn from the same distribution, and that its waveform is determined by a set of source parameters. So, for example, the same major axis of the binary black hole or neutron star, the masses, the co-moving distance to us, and so on. And that these sources together, once you've drawn them from this distribution, give you the probability distribution of the background. So if you look at a simulation of what this might look like, you have the strain as a function of time, and you see these fluctuations, which are basically a stationary process, because the evolution of the background is it follows much longer time scales than the observation time. And the goal of this talk is to model these fluctuations, these green ones and the red ones, all together, all of them together. Right, so just to very briefly say something about the physical model. So you can use any model for what I would say, but I'll just describe a plausible, simplistic one. So you take the same major axis to be log uniform. You take the formation time of the progenitors to follow star formation history, and then you take some power law mass function. And for the galaxy masses, you take some plausible Hello mass function, plausible Hello metallicity, Hello mass metallicity relation. And then you get all the properties you want for the black hole binaries after you formed stars and they died and became black holes or neutron stars. All right. The final component is how the wave is generated. So you can take the standard quadrupole formula, but you can do something even simpler for the Stoch, although everything works for the quadrupole formula. Just for the purpose of explanation here, I'm doing something even simpler. So you take a waveform that goes like 1 over distance. You can add this exponential damping for, let's say, beyond the standard model, dark matter models. Some of them can give you exponential damping, but for the purposes of this talk, you can just assume that this R0 is infinite, and then you have an oscillating function as a function of time. So this is the gravitational wave that a given source produces at the detector, and of course you evaluate it at the retarded time. Now, to calculate the probability distribution, you just need to combine all these random steps in the random walk. So you do that, and because they're independent, to get the final probability distribution of the sum, you just do a Fourier transform. And really, the only non-trivial thing is to calculate this this function g that appears in this Fourier transform. So you get a Fourier transform of this exponential. And it turns out that the function that goes into the exponential is the single source characteristic function. So you can calculate it from a statistical model of source parameters that for any statistical model that you want. And for the simple model that I described here, G has this form. So it has this these integrals of amplitudes and distance and other things. And then it also has this Bessel function. And it turns out that it is possible to do this Fourier transform analytically in some limits. So you can do it in the very small h limit, and then you get a constant. And you can do it in the very large h limit to derive the asymptotics and this and to test whether this background is a Gaussian background or not. So for large h, you know this is a Fourier conjugate to s, so you need small s. But it's a bit hard to expand this g at small s because it's not analytic. Nonetheless, you can proceed by using a technique called the Mellin transform technique, and you can show that g looks like this at small s when you can compute a and b for every model. And once you've done that, you know that you can plug in this expansion for G and get an expansion for P. And it turns out that the probability of observing a gravitational wave strain goes like the strain to the -4 at large values of the strain. And of course, you can do the calculation exactly numerically for the full probability distribution, and you can compare. So here you see the probability distribution of the gravitational wave strain normalized by something which has the right size. So here you can see that in the blue line, and then you can also see the power law as a red line and a Gaussian, which does not work. Okay. So far I've talked about how to do this for a single time, for a single moment in time, but we also want to calculate the probability distribution of a single Fourier mode. So I will assume that you observe the gravitational wave background for a certain amount of time, for a certain fixed time period t, and then you do a Fourier transform over this time period, and then you want to calculate the probability for each Fourier mode h tilde. So you do basically the same thing. The formula looks more complicated now because you have to account for each of the possibilities of the number of active sources individually to avoid divergences. And because now 3 amplitudes, so they can be complex numbers. So it's a 2D integration. But nonetheless, you still get the Bessel function, you still get the the same form, so you can do the same arguments. Now, one important thing to note here is that when you use your standard gravitational wave model, you know that the amplitude of a gravitational wave goes like 1 over distance, goes like frequency to the -7/6, but that's not it, right? It is only non-zero if it is emitted at such a moment in time that you observe it in the detector. So mathematically, that enters into the Fourier transform to get the Fourier transformed gravitational wave signal with the stationary phase approximation. So you have to require that the point where the phase is stationary indeed falls inside the observation window, or if you take the observation window and retard it to the source, then it has to fall within the retarded time observation window. So then you get another correction, which is this Heaviside function. You can write that analytically, and then you can plug this into G and calculate the G. So here is an example of what G looks like as a function of S for a given frequency. And here is an example of what the astrophysical model that I described here would give for the gravitational wave power spectrum. It's below the upper limit that we currently have, but if we get to A+ sensitivity, then it could potentially be detected. And then you can follow the same exercise. You can develop an asymptotic at large values of H, still goes like H to the -4. So you can see the probability distribution. So I would urge you to look at the blue line here. So it follows basically something that looked like a Gaussian until it settles on the power law asymptotic at large values of the strain, and likewise at the other frequencies. You can also add lensing and add whatever you want, and then repeat the same exercise, change the astrophysical model, etc. You can now remove bright sources from the astrophysical model, so you can decide that you don't include in this G function any source which would be individually observed. And then the form of the probability distribution of whatever is left out depends on the observation time. So if you observe for 1 minute, then you can see that the probability distribution settles on a power law, and then there is a cutoff. And the reason that there is a cutoff is because this here is dominated by individual sources that are just less bright than the threshold detectability for individual sources. And after you pass that, the only way to get a background amplitude, which is so large, is by constructive interference of many sources. And that's exponentially small in probability, so that you get an exponential cutoff. If you then increase the observation time, more sources fall into your observation, and then becomes closer to a Gaussian distribution. Now this H to the -4 power law, you can do a simple game, and you can look at LVK sources and check whether they obey this. So the simple game would be to take the distribution, the number of sources with an SNR equal to rho, and then check whether that is distributed by a power law. And it turns out that it's consistent with the power law, but the error bars are so big because we don't have many sources in all three so far. So that's good. So I'll finish here to leave time for questions. So this talk was about a method to calculate the probability distribution of the gravitational wave background strain fluctuations. I was focusing on stellar mass binaries, but the method can be generalized to other sources. And this revealed power law tail at large values of the strain, which of course means that the probability distribution is not Gaussian, and it can be used both for frequency space and for the time domain. Thanks very much, and I'm happy to answer any questions.
Thank you, Barry. Perfect timing. We have a hand up from Robert Rosati.
Hi, yeah, thanks for a nice talk. I was wondering, the non-Gaussianity you get in the background, is it more concentrated towards low frequencies or high frequencies?
Yeah, so it would be more concentrated towards high frequencies because at low frequencies you get more sources. Yeah. Thanks for the question. I should have mentioned that.
No, thanks. Yeah, it makes sense.
I had a question about the slide with the LVK events. So the error bar is the square root of the number?
Yes, basically.
And then you mentioned O3. I mean, I know they dominate, but is that only O3 or O1, O2, O3?
Oh, sorry, it's whatever you can find on the internet.
Okay.
Yeah. So what is done to get this plot is to take all 90 and then remove the ones which have SNR lower than 12, because it can be argued that maybe because they don't use SNR to decide whether there's a detection or not, then it's incomplete, let's say below 12, and then you do a histogram. Yeah, so you're left with about 40 sources, and then these are Poisson error bars, and they're very big. Yeah, but hopefully in the future we'll have better constraints.
Okay, thanks. Do we have other questions? Right, I don't see other hands up. So thanks again for the very nice talk, Barry. And
Thank you for the opportunity to speak.
Our pleasure. And we can go on to the second talk by Robert Rosati. And the title is Detecting Primordial Stochastic Gravitational Wave Backgrounds in the LISA Global Fit.
Okay. Yeah, so yeah, thanks for the organizers and everybody giving me the opportunity to talk here. So I'm a current postdoc at NASA Marshall, and talk to you guys today about some of the work we've been doing in LISA, and in particular our stochastic search and the global fit pipeline. So you've probably seen this plot many times during Amaldi, but I'll go through it briefly. So LISA is expected to see quite a few sources. In fact, they'll be signal dominated. You know, we'll really have quite a few sources overlapping in time and frequency nearly all the time. So we'll have a whole galaxy full of galactic binaries, several different populations of black hole mergers. And as well, we're guaranteed to have at least one stochastic source, the unresolvable galactic binary foreground. And if we're lucky, we might have an extragalactic background as well, some kind of, like we heard in the last talk. Or we might even have cosmology primordial source. So this is one of the LISA data challenges, just plotted as a time series, one of the three independent data streams you can get out of the LISA constellation. Just to kind of show you what the data roughly looks like. These bright purple spikes are the black hole in spirals. So they're so loud you don't even have to look underneath the noise. You'll just see them in the raw data. The galaxy population of binaries is the green curve here. So you can see the amplitude modulates as the LISA constellation goes through its orbit. The instrumental noise is just soon to be stationary and Gaussian. And the reason why we really have to do a global fit to all the sources in LISA is that just because they're all present at the same time and sometimes even the same frequency. You know, in ground-based interferometers, at least so far, the event rate is low enough that one source doesn't really interfere with another. But that's not going to be the case in LISA. They'll all interfere with each other, and you really need to jointly infer the parameters, or else you'll be biased. And if there's any stochastic sources, that'll need to be part of this global fit as well. And so the global fit pipelines in development for LISA, including the one my group has worked on, is based on blocked Gibbs sampling. And the essential idea is that you sample one group of parameters that are highly correlated with each other, and then freeze those, and then sample an orthogonal set. So you can think like you sample the galactic binaries all together, and then you freeze those and sample black holes for a little while and swap back and forth until you have a very low residual. That's the idea. And actually, there's many different components in the global fit. So there's this kind of Gibbs wheel we go around. So each independent sampler is working on its own, trying to subtract its sources and passing its residual onto the next one. And as long as you go around this wheel several thousands of times, you should converge to a good global solution. So here's what this looks like applied to that Sangria data challenge. It cost around $50,000 on Amazon Web Services computing time. That's more expensive than it probably has to be, but this is just a proof of concept, and we ended up running it 4 times. So the 13 or 15, I forget, black hole mergers are in pink here. Galactic binaries that were resolved correctly are all in purple here. And the residual, which is the part I'm most interested in for the stochastic search, is this light blue line here. And you see we have a little bump here, which is the galactic confusion noise left over from the undetectable binaries. And currently, this residual, it doesn't have the right correlations for that we'd expect from a proper signal in LISA. There are these 3 TDI channels in LISA, we call them, which essentially give you something like 2 independent right angle interferometers and an additional channel that's mostly noise dominated, at least under some fairly standard assumptions. Then you can, even though you only have one detector, you have these sort of 2 independent data streams plus a measure of the noise, so you can infer the stochastic background that way. And for the search, we've been using these stochastic templates. I've worked some in early universe cosmology. So I have a few templates we pulled from the literature, different cosmological effects, phase transitions or inflation, cosmic strings, things like that. The other thing we're doing is chunking the data in short time segments. I'll talk more about that in a second. In our pipeline at the moment, most of the heavy lifting is done by some C code. Then that's meant to interface with the rest of the global fit code, which is currently also in C. But all the results I'm going to present today were sampled in Python with this Aaron sampler from Nikos Karnisis and Michael Katz and collaborators. And we're chunking the data into short time segments just because it's not stationary. It's very not stationary. The galactic foreground is close to cyclostationary as the LISA constellation orbits and moves in and out of the antenna pattern. It's pretty well modeled by this analytic shape here in frequency. And then in every short time segment, we carry the constant parameters forward to the next time segment by using Gaussian mixture models for the, you take the posterior of one time segment and to be the prior of the next one. And so if you aren't familiar with Gaussian mixture models, they essentially are just a way to approximate an arbitrary distribution as a sum of different shifted and weighted Gaussians. And the basic idea is, yeah, like I said, we take the posterior from one time segment and use it as the prior to the next. So here's a comparison of using the Gaussian mixture models or fitting 4 months of data directly. As you can see, they're fairly comparable. They're independent noise realizations, so I think they overlap about the right amount. And then here is a, so these would be the 3 independent data channels from Lisa. And here I included, instead of using the real residual from our global fit runs, this is just a completely stationary injection that has roughly the right shape as a test. And you can see, we recovered all the injected parameters pretty well. Here I put all 4 months on top of each other. And as you go further along, you get better and better constraints. These are the noise parameters here in the top left. And these are some of the shape parameters of the galactic confusion noise. And this is the injected power law cosmology backgrounds. Unfortunately, when we try to do this with the real residual, we get something a little different. Even if I don't inject a cosmology signal, we find one, and that's due to this region here. Near the high frequency end of the galactic confusion noise. And so, yeah, you can't see it here, but these posteriors are missing the mark. They're not hitting the injected value. We thought maybe this is an inaccuracy in this particular shape we're using. This is the blue curve here is a spline, a best fit spline. To the shape of the confusion noise. This is good because it will probably switch to this eventually anyway, because we know there are other populations of the confusion noise. This paper came out recently talking about cataclysmic variables as another population that's not modeled here. But I think the real reason we're having trouble is because there are leftover sources that are, as you'd expect from real data, it's badly subtracted. And this is a Anderson-Darling score measure of Gaussianity. And so the data on the high frequency end of the galactic binary confusion noise is fairly non-Gaussian. And I think that's biasing our inference. Yeah, that's pretty much all I wanted to present today. Yeah, so in conclusion, Lisa, in principle, should be able to detect stochastic backgrounds because of this 3-channel construction. But yeah, this global fit residual is not Gaussian at all frequencies, so we'll need to take that into account properly in order to do inference with it in the pipeline. And I'll also mention I'm involved in another project, this blip pipeline for doing anisotropies in the stochastic background. That's the plan for future work, is essentially to take those non-Gaussianities into account and maybe switch to this wavelet domain for time frequency. Neil Cornish has worked on this pipeline as well, and he's very interested in that. So that's probably our.
Thank you, Robert. That was a very, very nice talk. And yeah, we have time for a few questions. Yeah, I was going to go back to the wavelets, but I guess you beat me with the final comment. You definitely have the expertise around to handle this with wavelets. I mean, there's this Bayes wave code developed by Tyson and Neil that could help. And then I had I think a question. I guess I didn't start it enough with the corner plots. There was some structure. The one, yes, this one. The K has a few bumps. Does that have any? Okay, sorry. The column with the K, there's the dashed line, and you recover that more or less, and then you have another minor bump around 600, and then something on the edge of these boxes. In the posterior for K, does this? I don't know. Does this have a meaning? Is this worrisome?
Yeah, it's this K. It's sort of it's sort of a frequency that goes into the sinusoid. So I think even this model is kind of degenerate. It's not really a I think people have wrote down other expressions with less parameters that do a good fit also. I think we're just hitting another mood of this sign here.
Okay, thanks. Then there's there are two questions from Chris Berry in the chat. What is the hope for finding multiple backgrounds, i.e. cosmology under an astrophysical foreground of merging binaries?
Absolutely. Yeah, we hope to be able to separate different components. You have a couple different handles, right? The spectral shape is different for those two backgrounds, and then they'll have different anisotropies. So the cosmology backgrounds, if it's loud enough to measure the velocity dipole, should be aligned with the CMB dipole, and so you could try to disentangle them that way. It would be tough. It would be tough without extra information to disentangle them, though. You would just measure the sum if they're both completely isotropic.
Okay, thanks for the clear answers. Thanks, Chris, for your question. Do we have any more questions? Okay. All right, then thanks again. That was a very nice talk, Barry. And we can move to the third talk by Chad Henshaw. There you are. Titled Probing the Horizon, Postmerger, Chirp Morphology and Parameterization. And there we go. We see your screen, your slides.
Okay. Hello, everyone. My name is Chad Henshaw, and today I'll be presenting some work that I've done towards investigating the morphology and parameterization of secondary chirps in the post-merger of the binary black hole gravitational wave signal. I'll begin by briefly discussing the origin of these chirp characteristics and their connection to the geometry of the final black hole horizon, which motivates this study. We'll then look at how the signal morphology changes depending on the orientation of the observer relative to the event. And then we will seek to parameterize this effect for use in future studies. So one of the lesser discussed phenomena that gravitational waves exhibit are chirps, or frequency spikes, in the post-merger of signals from binary black hole systems. This phenomena is particularly interesting because it offers a direct connection to the geometry of the post-merger final black hole horizon. A numerical relativity study from a few years ago showed that binary black hole systems with asymmetric mass ratio, here defined as Q greater than 1, will exhibit a characteristic double chirp pattern in the time frequency map of the gravitational waveform when viewed from an edge-on inclination, so inclination of pi/2. And one can see here that we have an initial frequency increase due to the in-spiral that peaks at the merger, and then a secondary frequency peak in the post-merger. As the mass ratio deviates further from symmetry, as you move to greater Q, this effect becomes more pronounced. In this study, it was further shown that the appearance of the secondary chirp is caused by a region of high outgoing radiation that sweeps across the observer's line of sight. They further show that this radiation field is connected to the curvature of the final black hole horizon, and as such, these chirp characteristics offer a link between the observable gravitational waves that we receive on Earth and the geometry of the distorted post-merger horizon. As such, if we can deepen our understanding of this link, then we have the opportunity to study the distorted horizon on a dynamical timescale. Now, accomplishing this will require two parallel efforts. The first is to locate signals within gravitational wave data that contain modal content beyond the quadrupolar 2-2 mode. Such search algorithms exist. I've listed two of them here. They're ongoing. They're constantly improving. And with the current influx of data from the fourth LIGO observing run and more advanced detectors on the way, I have little doubt that if such signals exist in nature, they will eventually be made manifest. The second effort is to deepen the connection between the signal and the horizon geometry, and it is here that we're offering a first step. When creating numerical relativity simulations, the data corresponding to the horizon geometry are typically not saved, or at least not offered in conjunction with widely available waveform models. If we start saving these data, then similar to how we have constructed surrogate waveform models, we can construct horizon geometry models that correspond to the waveforms. The problem is, numerical relativity simulations are expensive and time-consuming, particularly when you want to start including increasingly complicated dynamical effects like spin precession. To understand what parts of the parameter space we want to simulate, we're therefore motivated to parameterize the double chirp effect, which will allow us to then perform a correlation study with other parameters, such as those that characterize the precession. So in pursuit of parameterization, let's first understand how the appearance of the post-merger waveform changes as we vary the orientation of the binary relative to the observer. Here, we're using one of the GT waveforms, now called the Maya waveforms, which contain modes up to L equals 8. This setup that I'm showing here has a mass ratio of 10 with 0 spin, and we're going to begin at an inclination and phase angle of 0. In the bottom panel, we see the free space gravitational waveform, and in the top panel, we see the time frequency map. Now, keeping the phase angle fixed, we're going to vary the inclination from 0 to pi. So one can see that as we move to the edge-on observer orientation of pi/2, we see the appearance of a secondary frequency peak in the post-merger. Just from kind of watching this and from a visual inspection, you can see that the effect is most pronounced when we're exactly edge-on, like right here. So now let's fix our inclination at this edge-on orientation, the maximal orientation, where we can see an initial frequency peak that terminates at the end of the in-spiral. This is the merger, and a clear secondary frequency peak in the post-merger. Keeping this fixed inclination, we're now going to vary the phase angle from 0 to 2 pi, which is kind of like revolving the orientation of the observer about the merger center of mass. So now one can see as we vary the phase angle, we get a distinct region where there's a secondary chirp, like right here, and a region where there is not. What we also see is that the post-merger chirps are just a continuation of the chirping behavior in the in-spiral due to the mass asymmetry. This should not be surprising, as after the common horizon forms, we should expect the constituent black holes to proceed on their current trajectories towards singularity. That will affect the horizon geometry, and in turn, the radiation field, and in turn, the appearance of the secondary chirp in the gravitational waveform. Okay, so now let's begin to think about how we can parameterize this effect. First, let's talk about how we're finding these chirps. We make the time frequency maps that you have seen previously using the continuous wavelet transform, which is a convolution between the signal time series x of t and a wavelet psi. From the previous examples, we were using the Morley wavelet, which is a complex sinusoid modulated by a Gaussian envelope. Now, the continuous wavelet transform is often referred to as a mathematical microscope. And within this analogy, you can think of the wavelet as a choice of lens. At each time step described by the translation parameter b, we vary the effective sinusoid frequency and width of the Gaussian envelope by changing the dilation parameter a, thus narrowing the aperture of the lens. And then for each a, we calculate the convolution. Shown here is a cartoon of this process, where the green regions correspond to positive contributions to the transform and red to negative. The integral is then the sum of these areas. So in this manner, we can interrogate the time frequency space of the signal by varying our A and B parameters, and thus build the time frequency map pixel by pixel. Now, in some sense, the continuous wavelet transform is a check for similarity at each A and B between the wavelet and the signal. So if we're looking for chirps, then the appropriate choice of lens would be to add a forward chirp rate to the sinusoid. Our Morley wavelet now becomes a chirplet, which we can use to run the transform again. Here we now see that in the chirplet basis, the contrast of our frequency peaks compared to the rest of the signal has been enhanced. The overall idea for this parameterization is then to take the amount of transform content in the postmerger and divide it by the transform content of the rest of the signal. So to isolate the postmerger region, we can first create an effective one-dimensional f of t by taking the brightest pixel at each time step, shown here in purple. You can see that this purple line has two sharp up steps denoting the two chirps, and a drop-off denoting the end of the frequency evolution. We then define the left-hand boundary as the time of merger, given by the max waveform amplitude, and the right-hand boundary as the point where this f of t drops off. Our chirp parameter, kappa, is thus the ratio of the amount of transform content in this region over that of the entire signal. So, using this definition, we can now vary the inclination again, and we can see that the boundaries track the chirping behavior fairly well. Now, you may notice that the right-hand boundary is not actually tracking the f of t drop-off. In testing, we found that if we instead fix the width of our bounding region based on the maximal orientation, it makes the parametric behavior more consistent over the angular space. If we plot our calculated kappa over this range, we see that we indeed peak at pi over 2, and the shoulders here indicate a sort of window of relevance where the double chirp effect becomes prominent. We can likewise do the same sort of calculation for varying the phase parameter. Here you can see the advantage of using the fixed window as the purple f of t line becomes more erratic in different parts of the parameter space. But by using this fixed window, we can get a pretty good read over the parameter space, and we can track the appearance of the secondary chirp fairly well. If we plot our value of kappa over this range, then we can see we can get a reasonably clean identification of the maximal chirp region. Okay, so it's important to note that the original numerical relativity study and the demonstrations that I've just shown encompass only the most basic parameter space, that is quasi-circular and spiral with zero spin. So this is all well and good, and we can get a consistent read over the angular space for this non-spinning case. However, now let's think about the spinning case, or really let's think about the precessing case. If either of the black hole spins are misaligned relative to the direction of orbital angular momentum, then the orbital plane will precess about the direction of total angular momentum. And as such, the orientation of the orbital plane relative to an external observer will vary over the course of the inspiral. Luckily, the orbital plane precession is one of the system dynamics that we can reduce to single number effective parameters, such as the parameter chi-p that characterizes the single largest misalignment in the binary, or the more recently developed parameters average chi-p or root mean square chi-p that preserve the misalignment information from both spins. If we want to understand how the chirp parameterization behaves in general, we can use these parameters as a map for the precessing parameter space. To this end, we can make use of the newer waveform models that include both the effects of precession and higher order modes, such as this effective one-body model. Such models allow us to scan over a wide, continuous intrinsic parameter space and see how the chirp parameterization responds. At each point in the intrinsic parameter space, we can then vary the orientation parameters to determine the direction of maximal emission. Now, when we varied the phase angle earlier, we saw that the double chirp pattern emerges as essentially a continuation of the in-spiral behavior, visible only at the proper orientation, as the two constituent black holes proceed on their in-spiral trajectories towards singularity. In the precessing case, the black hole trajectories are not a simple fixed plane in-spiral. The plane through which they're in-spiraling changes its orientation, and so they evolve through a more complicated helical trajectory. Again, once they get close enough for the common horizon to form, we should expect this trajectory to continue until singularity. As such, we should also expect the horizon geometry to correspond to this trajectory, and we can conjecture that the double chirp should trace a more complicated pattern on the sky of the final black hole. So let's look at the entire sky. So first, let's look at the zero spin case here at mass ratio of 4. We plot our value of the chirp parameter kappa over the sky of the final black hole. We see something quite similar to the 1D angular variation plots from earlier. The distribution of kappa is symmetric and diffuse, with the maximum value sitting right on the equator, corresponding to an inclination of pi over 2. So now let's look at the precessing case, and let's just go straight to the maximal value of precession. So here, with a chi-p value of close to 1, same mass ratio, we see that instead of the equatorial symmetry that we saw previously in the zero spin case, we have a maximal chirping region with a slanted orientation that breaks the plane of symmetry. It's easier to compare if you put these right next to each other. So here you can see that the precessing case has a more concentrated chirping region. And as we conjectured earlier, this region breaks the plane of symmetry in accordance with the more complicated in-spiral trajectories. Additionally, the direction of largest kappa does not lie on the equator. So using this parameterization and full sky approach, we can therefore identify the orientation of strongest post-merger chirp emission. You can then take this orientation and generate the waveform, and now we see the emergence of a strong double chirp pattern. Okay, so let's recap. There is a direct link between post-merger chirps and the geometry of the distorted post-merger horizon, but this link is not yet well understood. Here, we offer a first step towards deepening our understanding of this connection by parameterizing the double chirp effect using the continuous wavelet transform. Our next tasks are now to apply this parameterization to a wide parameter space that includes varying mass ratios and transverse spins. We do this by using modern waveform models that include these effects and higher order modes. Such models allow us to draw correlations between the chirp parameter kappa and parameters that map the precession. We can also learn more about the modal content of the double chirp features by progressively scanning over different compositions of higher order modes. So by exploring the parameter space in this way, we can discover targets and make predictions for follow-up numerical relativity studies, which can output not only higher fidelity waveforms, but also horizon data. If enough such data can be generated, then similar to how we can interpolate NR waveforms into approximate models, it should be possible to aggregate horizon data into horizon models directly linked to their gravitational waveforms. as we accumulate more gravitational wave detections and the higher order mode search effort continues, we can push the development of these methods forward in parallel. In doing so, we seek to study gravity in its strongest regimes and move towards using this connection between signal and horizon geometry to study the final black hole directly with gravitational waves on a dynamic timescale. So with that, I'll thank you for your time and I'll take any questions.
Thank you, Chad. That was a very exciting talk. I'm open to seeing hands up for questions or questions in the chat. By the way, I forgot with the previous question, I'm able to ask you if you want to be unmuted, if you want to pose your questions orally without me having to read them. In the meantime, I was going to ask if, well, first of all, very, very interesting. This is far-fetched, but do you think if you consider binary neutron stars, you can somehow readapt what you're doing to look for, you know, secondary peaks
in the BNS postmerger?
Yes, for the hypermassive neutron star.
Please,
for the normal, for the oscillation of the hypermassive neutron star.
So something similar, I think, could be done. In fact, one of the other grad students at Georgia Tech is working on something similar. Megan Arrighetti, she has a poster at Amaldi that I recommend you check out, where we're using similar methods with the continuous wavelet transform to look for post-merger BNS signals. So it's definitely adaptable.
Okay, interesting. Yeah, that would be, I guess, higher frequency and anti-chirping, I guess, not necessarily chirping. Okay, and then I don't know if this is relevant, but you've talked about mapping, you know, what you're seeing to parameters. Have you considered different ways of defining chi-p? I know there's, you know, there are ongoing debates on what the best definition of chi-p is. Is this relevant for what you're doing?
It's a little bit relevant. I go back to, so for example, for this case, I'm using our standard definition of chi-p here instead of the more recent definitions of, for example, chi-p average or root mean square chi-p, primarily because at higher mass ratio, they're essentially the same. We showed this in a paper a few years ago that at higher mass ratio, chi-p and, for example, average chi-p, which is the two-spin precession, essentially converge because the effect of the less massive object in the binary is just lesser at higher mass ratio cases.
And when the differences are greater, though, I guess the higher mode emission is not as strong, right? When these two definition or values you get with these two definitions, when they're different and the dynamics becomes erratic, I think that's happening in corner cases of quasi-equal mass binaries. Is that correct? And so you
you do see strong differences in equal or close to equal mass cases, but what you don't see is double chirps. You need to have the high mass ratio cases. So I think it would only be relevant if you're looking at something like close to mass ratio 2, in which case you would want to use, for example, average chi-p, which is more has higher fidelity towards the actual processing dynamics.
Okay, thanks. Any other questions? All right, if not, I'll thank Chad once more. We're early on our schedule. Nevertheless, we'll resume at 10 past the hour. Hopefully that works for all the time zones involved, with the talk on black hole spectroscopy. So what is it? 10 past 2 UTC. I think I made that. No, 10 past 3 UTC. We'll reconvene for the fourth talk. Thanks. So welcome again to the parameter estimation session. We're resuming after a break, and our first speaker is Sizheng Ma. with a talk titled Black Hole Spectroscopy by Mode Cleaning.
All right. Hello, everyone. My name is Sizheng Ma. Today, I will be talking about a new method for black hole spectroscopy. To get started, let's consider a binary black hole merger. Its random part corresponds to the oscillation of the remnant Kerr black hole. To the leading order, this process is governed by the Stochastic equation. Quasi-normal mode is an important concept within this topic. It describes the characteristic oscillation of the Kerr black hole. Due to the no-here theorem, a quasi-normal mode of a neutral Kerr black hole is fully determined by its mass and spin. So if we can detect a quasi-normal mode from a random signal, then we can infer the remnant properties. If multiple modes can be detected at the same time, then we can test the no-here theorem. And this method is known as black hole spectroscopy. So here we would like to propose a new method for this topic, which is based on a frequency domain filter, and we call it rational filter. The core idea is to highlight subdominant modes by filtering out the most dominant ones. Let's consider a toy model to help you understand the logic. This is the excitation of a single quasi-normal mode. Capital theta is the Heaviside step function, and h of t is plotted as this black curve in this panel. Now we can use this time domain operator to remove this specific quasi-normal mode. But in practice, numerical differentiation leads to noise, so we'll do this in the frequency domain. So, but you may notice that this term is linearly omega, so any high frequency noise could easily contaminate our random analysis. So we further normalize it with this complex conjugate. So this is the final form of our rational filter. Then we apply the filter to h of t and obtain this red curve. So you can see this random mode is flipped to the other side. But if we restrict ourselves to the original random region, you see this mode is removed completely. An interesting application of this method is to look for second-order quasi-normals. You know, to the leading order, a random signal is the superposition of linear quasi-normal modes. At the second order, there will be couplings between those linear modes. For example, for a 5-5 harmonic, there will be a contribution due to the coupling between 2-2 mode and a 3-3 mode. To see this, we took the 5-5 harmonic from a GW150914 like numerical relativity study, which is this black curve. Then we filter out all the linear quasi-normal modes and obtain this red curve. You can see there are a few oscillations that are consistent with this green dashed curve, which corresponds to the evolution of this 220 plus 330 effect. So this comparison shows verifies the existence of this quadratic effect. I hope this example can give you a rough sense on how this method works. So basically, after filter out the most dominant modes, we can start to visualize the existence of those modes without going through the normal least square fit. In addition to this time domain analysis, our method also works in the frequency domain. Here we still use this system, for example, and this time we focus on the 2-2 harmonic. We FFT its random portion and obtain this black curve. You may notice that there is a huge peak centered at 220 fundamental frequency, which is consistent with our understanding because 2-2 fundamental mode is the dominant mode. Then we can add the filter of overtones to remove them. After filtering out 3 overtones, we obtain this red curve. Now you can see there is the new peak starts to show up, which is different from the original 2-2 mode. And meanwhile, you may notice that there is a tiny wiggle at the 0 frequency. Then we continue to filter out more overtones. After removing 7 overtones, we obtain this gray curve. you may notice that there are two peaks over here, and it turns out that the right one corresponds to the 3-2 mode due to spherical and spheroidal harmonic mixing, and the left one centered at 0 frequency corresponds to a constant value in the waveform. And then we can add the 3-2 fundamental mode filter and its overtone to remove this peak. After filtering out those two modes, we obtain this red curve. Now, two new peaks show up, and you can check that they're consistent with 330 and 440. Further adding those two filters can remove those two peaks, and we obtain this green curve. And this time you may notice that there is a bump in the negative frequency band corresponding to the 2-2 retrograde mode. And there is another bump over here corresponds to 2-1 mode. All right, after filtering out all those quasi-normal modes, let's go back to the time domain again. You see the original rain-down modes are gone completely, almost completely. And we are left with a constant value, which is on the order of 10 to minus 5, which is pretty close to the numerical relativities error. And there are still some oscillations. We are not sure whether they are physical or not. Let me recap a little bit. So this rational filter offers a new way to identify quasi-normal modes. And compared to the Euler list square fit, our method is bound to filter out a quasi-normal mode without the need for its mode amplitude and phase. So it is supposed to be more stable. In addition to the analysis of numerical relativity waveforms, another interesting question we could ask is that whether we can use that to analyze real observational data. And the answer is surprisingly yes. So a new feature introduced by our filter is that we can construct a new two-dimensional likelihood function in the time domain for the rain-down portion of the waveform. We need only mass and spin to construct any rational filter. And after filtering out enough modes, we expect that the rain-down part of the waveform is consistent with pure noise. So this idea leads to a likelihood that is a function of only mass and spin. And it's interesting to note that after this function is always two-dimensional, no matter how many quasi-normal modes are present in the waveform. As a result, there is no need to use MCMC to draw samples. Instead, we can directly plot the likelihood as a function of mass and spin. So taking GW150914, for example, those two heat maps are from our filter analysis, including only the fundamental mode on the left and the fundamental mode plus the first overtone. For comparison, we also repeat the normal MCMC method. Those two white dashed contours enclose the corresponding 90% credible regions. So you can see both methods are consistent. Other interesting feature introduced by the filter is that we can first filter out some quasi-normal modes as a pre-processing step, and then use the normal MCMC method to fit for the remaining modes. This method is interesting, especially when we are searching for a weak mode with the presence of some stronger modes. Quasi-normal modes are not orthogonal. In the presence of some stronger modes, our search may be impacted. So if we first filter out those stronger modes, then the result should be less biased. For GW150914, we could first filter out the fundamental mode and fit for the first overtone alone. And this is the posteriors of mass inferred from the first overtone as a function of starting time. You see we can still extract meaningful information from the first overtone. The existence of the first overtone in this event has been controversial. A concern in the literature is that this two-mode analysis starts from 2.3 m after a peak, which seems to be too early from a theoretical point of view. Based on numerical relativity studies, one had to wait at least 18 m to let other modes settle down. So how would we reconcile this discrepancy? So for the final part of this talk, I would like to provide my understanding. I think the key feature is that the unmodeled contents need to have enough accumulated SNR to bias the inference of Meson spin. In the presence of statistical uncertainty, we may be blind to the systematic bias. Here, I don't have time to go into details, so I would like to refer to this section of our paper if you are interested. Based on our numerical relativity analysis, we can have such SNR ranking. For actual detections, we have to take the detector noise into account. So then we will have the following scenarios. First, when noise is between the fundamental mode and the first overtone, then we need only this 2-2 fundamental mode to analyze the data, and we don't need to deal with other modes. If the first overtone is stronger than noise, then we have to use 2 modes, but we are still blind to other unmodeled residual. Finally, if the residual is stronger than noise, then we have then failing to model the residual may cause systematic bias for in the inference of those 2 modes. For GW150914, we could fit the rundown of this event start from 7M after a peak with only the fundamental mode, and you see there is no significant bias in Meson spin, even though the numerical relativity studies shows that we have to go beyond 47M to let other modes settle down. And if we move our analysis from 7M to 2M after the peak, then we are under the second scenario. And now this time we have to use 2 modes to analyze the data, but we are still blind to the residual. So we don't need to include that into our studies, even though we are starting from 2M after the peak. However, this doesn't mean that we can safely recover all the mode information at early times. We found that the fit for mode amplitudes is quite sensitive to the unmodeled residuals. To see this, we can inject a numerical relativity waveform into noise and prefer a normal MC method with 2 quasi-normal modes. And on the other hand, since we are dealing with numerical relativity waveforms, we could prefer a least square fit to obtain the true value of mode amplitude. And after comparison, we found that the inferred mode amplitude is quite different from the true value at early times. Instead, it is consistent with the result obtained from a 2-mode fit, two mode least square fit. And we know that this 2-mode fit for a wave for NR waveform at such an early time is not correct. As a result, the MC-MC inference of mode amplitude is biased, and it is less stable than the inference of frequency. This is because the amplitude inference is dominated by the first wave cycle rather than the accumulated effect. Recall that in order to have a frequency search, we need to have long enough waveform and long enough cycles. So we have 2 direct consequences. First, the inferred mode amplitude doesn't follow an exponential decay evolution. And second, the amplitude is smaller than the should-be value. So we need to be very careful while using the statement such as overtone's amplitude is consistent with 0 within X sigmas to rule out the existence of an overtone, and because the amplitude search is biased. So my major takeaway message is that in low SNR regime, the frequency search and the amplitude search have quite different features. And with our current detector sensitivity, maybe instead of asking whether we have detected the first overtone or not, maybe it's more reasonable to ask how much information we could extract from the first overtone. And with that, let me stop here and take any questions. Thanks.
Thanks for the very nice talk. We have hands up for questions. Pierre has a hand up. I have to unmute you. Let's see. Whoops. Sorry. I remuted you. Whoops.
Okay, sorry. Can you hear me?
Yep.
Okay. First, thanks for the very nice and very interesting talk. I especially appreciated your conclusion message on what is a relevant question we should really ask about the first overton. Now, I was curious about if you can use rational filter method to check how much we can actually perform spectroscopy using the overtones or even beyond the first overtone, by like if you have tried to filter out modes which do not have exactly the GR frequency.
Yeah, that's a very good question. So if the frequency we imposed in the filter is slightly off or even much larger off than the target mode, this system will have worked out the analytic expression for this system. So it won't change the start time of this mode. And it won't change the evolution, by evolution, I mean frequency and the damping time of this target mode. The only changed thing is the mode amplitude. And more specifically, the mode amplitude is reduced by the wrong filter. And that reduced factor can be computed analytically. So after filtering out, for example, fundamental mode, then we will reduce the amplitude of the first overtone, but we know what the reduction factor is, so we can take that factor back. Does that make sense?
Yes, but if you apply this to the numerical relativity waveform, the same way that you have shown when you remove the modes one by one from 0 to 7,
yep.
Do you, like if you try to do that with modified frequencies, do you explicitly recover a louder residual signal?
Oh, no. If for numerical relativity waveforms, if the frequency is wrong, for example, the overtone frequency is wrong, that peak is still there. I cannot remove that with the wrong filter.
Okay.
So it's quite sensitive to the filter we impose.
Okay, thanks.
Hey, I don't see other hands up. Last call for questions. If not, let me thank the speaker once more, Sizheng Ma. That was a very nice talk.
Thanks.
And next we have Inferring Properties of Dark Galactic Halos Using Strong Length Gravitational Waves by Song Wang. I see you.
Good. Okay, hi everyone. So thank you for attending this talk. So today I'm going to talk about how to infer properties of dark galactic halos using the strongly lensed gravitational waves. Okay, for the outline of the contents, so I will firstly introduce the motivation of this work, that is the what and why we want to estimate the properties of dark halos. Then shortly explained what are the strongly lensed gravitational waves and how to analyze them using the joint parameter estimation and the rejection sampling. And finally, I will show you the results from the several mock GW signal simulations. Okay, so there are some representative properties of dark halos. So there are total masses, density profiles, elliptic stills, and also some substructures. And these properties can be parameterized as the lens parameter theta L, as we will treat the dark halo as a gravitational lens. So as known, the mass or the potential well of halo strongly correlates to the star formation rate. So the stellar mass functions and the stellar mass function properties of a supermassive black hole at the center of galaxy, so the AGN and quenched fraction of a galaxy as well. So if we can estimate the lens parameters accurately, then we can better understand the galaxy evolution, formation, and quenching. And furthermore, if we extend to the galaxy cluster scale, we can also constrain the halo mass function by investigating the galaxy groups or clusters at various redshifts. But actually, there are lots of applications, as you can see below. So there are many papers, but this is beyond this work, so I will skip the details. So in order to estimate the lens parameters of dark halo, we need any detectable things from which we can extract the parameters. So we focused on the strongly lensed gravitational waves. So let's see the strong lensing first. So similar to light, the gravitational waves are also lensed by the intervening massive object on its path. But however, when it comes to the strong lensing regime, there are some different characteristics between the light and gravitational wave lensing. So first of all, the strong lensing results in the magnification of flux of light. So the apparent distance to the light source is proportional to 1 over the magnification factor. And for the GW, the strong lensing results in the magnification of GW amplitude. So the apparent distance to the GW source is proportional to 1 over the square root of magnification factor. And also, we can instantly know that the lensed light image is distorted, as you can see the left top image. On the other hand, the waveform morphology of GW does not change in the strong lensing regime. So the just phase shift occurs. And lastly, we cannot instantly estimate the time delay between the lensed images of light because we just see a map of see a snapshot of an area. So of course, yeah, so it is it. And it can be a different story if we can transient if we detect the transient sources such as the supernovae and gamma ray burst. But on the contrary, we can measure the time delay instantly between the lens GW images very accurately, and it can be helpful to estimate the mass of the lens. Okay, and let's see how the GW signals are strongly lensed. So based on this Takahashi Nakamura paper, the lensed signals can be created by multiplying amplification factors by the original unlensed signal. So since gravitational wave is the geometrical optics approximation is valid for the GW in strong lensing regime, so we do not need to consider the complicated wave optics if we ignore the substructure of the lens. So we can just use this amplification factor function. So here mu is the magnification factor, and T is the Fermat potential, and N is the Morse number, which is related to the phase shift of the waveform. So therefore, for GW, only luminosity distance and coalescence time and phase will change due to the lensing effects, and the other source parameters remain the same. Okay, and next, to simulate the lensed GW signals, we assume the various lens models. So we use the 6 lens models. The 3 are the axially symmetric lens as shown at the left-hand side. And so the point mass, SIS, and NFW density profile. So even though the point mass model is not suitable for describing halo, so we consider it to compare our work with the previous works. So for the point mass and SIS, they can only produce the double images, and NFW always produce the triple images. And as you can see, the lens parameters of axially symmetric lenses are relatively simple. At the right-hand side, so the more realistic lens models are introduced. So SIE, SPAM, and elliptical NFW density profile. So they are not non-axially symmetric, so elliptical. So more than double images can be produced depending on the lens parameter combinations because the non-zero ellipticity makes caustic have a finite area. So speaking more about the spammed lens model, so if the density slope parameter T is equal to 1, then it's identical to the SIE. If T is larger than 1, the potential well of a lens becomes steeper, and when T approaches 2, then it becomes identical to the point mass. Okay, so for each lens model, we may want to know what lens parameters can occur the GW strong lensing. So we select specific lens parameters which can produce multiple images and then save the selected parameters in this large data template bank. So the example of the spammed model is shown in the red box. So firstly, we solve the lens equations for all lens parameters chosen from this physically possible parameter pool. Then, if we if the number of solutions of lens equation is less than 2, the parameter is abundant. If it gives the 2 or 4 solutions, then we calculate the corresponding magnification factors and Fermat potentials of each image and save all these 3 values in a template bank. So we call this triplet as a large theta, and we use the bank of large thetas for the reject sampling in the future. By the way, using those accumulated lens parameters, so we can also calculate the strong lensing cross-section. So actually, it is informative to investigate with which model is the most efficient to produce detectable lens GW signals, because this can be helpful to the hypothesis test and the model selection in the future works. So based on these given equations, we calculate the sigma 1.0, so the area where at least 2 GW images have magnification factor larger than 1. So our conditions are the same here, just the lens model is different. So as you can see, the figure at the right-hand side, the denser lens model is more efficient for generating multiple images. So actually, it is well known that lensing cross-section of SIS is larger than one of the NFW on EM side. Okay, and for the denser lens model, low ellipticity is more efficient for producing multiple images, but on the contrary, the high ellipticity is more efficient for strong lensing for the sparser lens models. So now I show how to simulate the mock lens GW signals in our work. Okay, so for the original lensed signal, we assume the GW 1509-14-like binary black hole with the luminosity distance at 3000 megaparsec and specific coalescence time and phase. So we use this lens signal to make the 8 sets of lens signals with these 8 kinds of lenses. So as you can see the table at the right-hand side. So we use these lens parameters and Reischke lens mass to have the 8 different lensing potentials. So for each potential, we calculate the magnifications and Fermat potential and make 8 sets of lens signals which have these altered source parameters. So here, So now we have the mock lens GW signals. So the next step is reversely infer the lens parameters from the lens signals using these joint parameters and rejection sampling. So let's see first the joint parameter estimation. So for simplicity, I will just talk about the point masses case only. So as I mentioned before, a point mass produced 2 lens signals, so HL1 and HL2. So we used the Golem pipeline to conduct the joint parameter estimation, which gives the posterior of the relative magnification factor μ, time delays between the lens signals, the delta t, and the difference between the Morse number of each lens signal, so the delta n. So Golem is the Bilby-based pipeline. So regarding source parameters, it follows just the Bilby configurations totally. So and the result posteriors obtained from the Golem runs are shown at the right-hand side. The 2 posteriors are converged to the injection value well. So we will use these for the rejection sampling. Note that the delta n is a discrete number, so 0 or 0.5 or 1, so I intentionally didn't put it here. Okay. And next, we perform the rejection sampling. So we use the Gaussian corner density estimation to obtain the continuous probability density function P μ from the posterior sample of μ. Then, in order to perform the rejection sampling, we set up uniform distribution as proposal distribution, so QL, from which to sample value is μ. And then we match the maximum values of the Q μ and P μ by identifying the multiplicative constant m to satisfy this inequation. So for all μ points. Okay. And we now use the theta template bank, which contains the ordered triplets of lens parameters and corresponding magnifications and Brahma potentials. So from each triplet, we can get the relative magnification factor mu-L. So it can be like the mu2 over mu1. Then we sample a pair of mu-L, D within the MQ mu-L distribution, so this yellow box. So if the sampled point is below the P mu-L distribution, the point is accepted as this green dot is, otherwise rejected as the magenta dot is. Okay, and lastly, to repeat the sampling until we get robust results. Okay, and from the accepted large theta triplet, the theta L groups will be the posterior points of the lens parameters, and delta large T groups are used to estimate the redshifted lens mass posterior with the previously measured time delay through dissipation. So this can be the final one. So I will show you the final results for the two simple lens models first. Okay, so this is the result. The colored histograms are obtained from the above process, and the black solid line ones are from analytical method. So the analytical method means that we directly convert the lensing observables to the lens parameters and redshift lens mass, because for a simple lens model it's possible. So for both cases, posteriors peak at the injected values, which shows the successful inference on the lens parameters, and these almost identical plots of this colored and black solid line histogram show the validity of the above rejection sampling. Okay, next, let's see the complicated lens model cases. So among the 6 cases using complicated lens models, the results for the SIE, SPAMD, and NFW with double images cases are shown here. So for the NFW, the posteriors are relatively well converged to the injected values, but it's not for the elliptical lens models. So this is because the degeneracies between the axis ratio Q and other lens parameters are strong. So even with triple and quadruple images, the axis ratio posteriors are a little bit better constrained compared to double image cases, but it is still not acceptable. So therefore, we consider a situation when the additional electromagnetic wave observation is available. So as demonstrated in the Hanasela et al. Paper, the localizing the source and lens galaxy is more feasible with more than double images, because the more GW and lens host galaxy images enables us to narrow down the sky area, including the GW source and lens galaxy. So we can find we can specify the lens galaxy using like SDSS catalog or other galaxy catalog project. So once we specify the lens, we can know the shape of the lens. So we assume that the axis ratio Q of the galaxy halo can be confined to within the plus minus 5%, so total 10% error ranges. So the result posteriors for all elliptical lens models almost peak at the injected values. So therefore, for the complicated lens model cases, the more than double images and additional electromagnetic observations are necessary to constrain the lens parameters. So here is the conclusions. So we demonstrate that the strongly lens GW signals can be used to estimate the properties of black halos, and we adopt the joint PE and rejection sampling techniques to recover the lens parameters, so the properties of various lens models. So for the simple lens models, the lens parameters can be recovered well with only the GW information, and for the complicated lens models, the lens parameters can be recovered well with the more than double images plus the additional EM observations. Actually, the accuracy of the inferring can be improved when we detect the high SNL lens signals so that the mirror posteriors can become narrower, and when we can more precisely measure the axis ratio of the specified lens galaxy. And for the future work, all works will be integrated into one pipeline soon, and then we will develop this work with the Gravity Lens pipeline, and the LVK lensing group plans to conduct lens model dependent lensing search use this pipeline. So it is expected to be available in O4B. And also, we will extend this technique to the more complicated lens models, such as the macro plus micro lens system, a lens plus extra shear, and also the multi-lensing systems, which means that the lensing occurs multiply. And finally, we will apply this technique to better constrain the Hubble constants. So you can see this paper and discuss it offline. I think the time is late. Okay, so thank you for listening.
Thank you for the talk. Do we have questions? Okay, if not, I will start with one. Can you go back, I think, one slide or two? I can't remember.
Sorry?
Could you go back one slide?
Yeah.
Yes. So again, in these corner plots, in the middle one, it looks like your posterior for T is, I guess, railing against the prior or something. In that histogram, yes, you went over it with your mouse.
Yeah.
Is that
so?
Yeah. Can you comment on that?
Okay, so this T is the parameter of the density slope of the halo. So I use just a uniform prior distribution, and this is the posterior distribution after you filter some unnecessary one and just like survive the point samples. So this result is here, and the injected value is around the 0.8, and it picks around the true value. So I think if we confine the axis ratio, then the other lens parameters like y, the source position, density slope, and redshift lens mass can be constrained very well.
Okay, and then in a few of these 2D posteriors, like the one on the left, and there were a few cases earlier on, you have these like whiskers of points.
Yeah.
I don't know if it's clear which ones I'm talking about, like the purple bottom left corner plot. Yes, there are these little traces of points on in the top left quadrant.
Yeah.
Here, I guess I can give you coordinates: 0.17 and 12.10.
3.17.
Yes, and then go up with the S. That happens in a few plots. Is this something you can comment on? Often you have these extra lines.
Oh, okay. So for this one, so this is because of the, we don't use the zero noise when we inject a signal to the detector frame. So it is because of the like real noise, because I use the over Gaussian noise. So.
Okay, thanks. Any other questions? If not, I'll thank both right? Yes, both speakers again for the very nice talks. And we can break for 11 minutes till 1600 UTC, and then resume with two final talks for this session. Okay, time to restart. We have final two talks for this session on parameter estimation. And I'd like to welcome Verónica Villa-Ortega, who will be presenting a talk with title Estimating Binary Source Properties in Very Low Latency via Post-Newtonian Parameter Space.
Thank you, Francesco. So yeah, I wanted to give you an introduction to this work that we have been developing in the University of Santiago de Compostela with the help of Frank Holm from Hanover. So the motivation for our work is mainly to be able to be fast following up possible signals with neutron stars. So we all know that the only signal with an electromagnetic counterpart had a gamma ray burst that we observed 2 seconds after the merger, but also we could observe a kilonova hours after the merger, and this could have been sooner if the alerts were faster. So the challenge that the low latency searches are facing now is to identify rapidly and send these alerts to the electromagnetic and neutrino observatories. If we see the timeline of the collaboration alerts, the parameter estimation lies a bit low in the alert system, and we are working in a way to making it faster. So I work in one of these low latency searches in PyCVC Live, which is an online all-sky model search for compact binary coalescence. This search uses match filtering using a bank of templates, and each of these templates has component masses and spins. And we are making use of a new tool of PyCVC Live, which is the SNR optimization that can find the trigger that maximizes the SNR. This SNR maximization is not working now for 04, but hopefully will be working at the future. And the thing we have done is to implement a very rapid, under a minute, estimation of the uncertainties in binary masses and spins relative to these maximum SNR points that we got from the search. And the way we explore the parameter space is to use this trigger point from the search as the maximum likelihood point in the physical parameter space. So the maximum likelihood point in masses and spins parameter space. Then we generate a set of initial samples. In this case, we are generating 10 million initial samples. And we compute the distances in parameter space between them, this maximum likelihood point and all the samples that we generated using waveform differences that we can relate to the mismatches between these different waveforms. The first thing we did to make this faster was to make use that the knowledge we have about the chirp mass, and we studied in a previous work that the chirp mass is well measured by these low latency pipelines, and that for lower chirp mass events that we are more interested in, the relative error in chirp mass was usually low. So we restrict the samples to be in an interval of chirp mass instead of the whole space of the masses. So then the way we are generating samples is we are computing the chirp mass from the trigger template and generating samples uniform in this chirp mass contour and the mass ratio. So for example, in the case of the trigger of 200115, these will be the samples that we generated. And in the case of the spins, we are using the usual parameter estimation priors that are uniform in spin magnitudes and isotropic in spin orientations. So again, the yellow star would be the trigger for this signal. And now that we have a lot of samples, we are going to compute the mismatches between these samples and the point from the search. And yeah, again, we do that using these distances in parameter space. And we are using the Fisher matrix approximation that allow us to approximate these waveform differences by the multiplication of the Fisher matrix and the differences in parameters. And here is where the next trick comes. That is that we are going to change our parameter space, and we are going to consider a higher dimensional parameter space. So instead of using the physical parameter space of masses and spins, we are going to convert these samples to a post-Newtonian parameter space. And the reason we are doing that is that in this space, the Fisher matrix is almost flat. So if you see the expression for the Fisher matrix, it's independent, almost independent of the post-Newtonian parameters, and that allow us to compute the Fisher matrix only once for the whole calculation, and we don't have to compute it for every sample. In the plots of the right, you can see how the waveform manifold in a higher parameter space of post-Newtonian parameters is close to flat. So the differences, the waveform differences in this space are easier to compute. In this slide, I'm just showing an example of the mismatches we computed for the NSVH trigger. So in the plot of the left, you can see how the lowest mismatches belong to this very narrow contour of chirp mass, as we expected. And in the plot of the right, you can see a bit of the structure of the correlation between chi effective and eta. But with the mismatches, we need to go a bit further, and we are going to obtain the posterior probability plots. And we do that calculating an approximate likelihood that is related to the SNR of the event squared and the mismatches that we previously computed using the Fisher matrix and the difference between samples and the maximum likelihood point. And once we have this approximate likelihood, we are going to discard all the samples that are not useful. But first to that, we have to keep in mind that the samples we have generated are uniform in chirp mass and mass ratio, and not in component masses. So we are going to apply our weighting factor, Jacobian of the two prior distributions, to make our samples uniform in component masses. And when we have that, we can compute an approximate posterior that is proportional to this Jacobian and the approximate likelihood, and reject do a rejection sampling to keep the samples that are close to the value at the trigger point. So, well, basically we want to keep the samples that are close in likelihood to the maximum likelihood point. And once we have done that, we can draw the posterior samples. And in this slide, I'm just showing the results for one example, comparing the posteriors we got using this method in orange against the posterior samples that were distributed in the WTC 3 catalog. So as you can see, what we wanted initially was to get an estimation of the errors in masses and spins, but we are also close to get the maximum likelihood point at some cases. And again, this is done in less than a minute compared to the whole P analysis. We have been testing this method also in the mock data challenge data, and we have run the code on hundreds of these injections that were recovered by passive slide using the SNR optimization. We have applied some thresholds to ensure, well, that the injection recovered will cost an alert. Also, we have restricted the chirp mass to stick with the events that we are more interested with, that more interested at, that are the lowest M-chirp events, and the SNR to be over 10. And we recovered almost 700 injections, and the distributions of masses and spins are in the plots at the right. So they are almost all PNS and NSVH as we expected. And well, these are the results for one example of these injections, where the injection value lies close to the maximum likelihood in the posteriors that we generated. With all the injections we recovered, we made some PP plots. These will be the ones from the masses, where you can see that some bias is appreciated, but it's not very shocking. And in the case of spins, we note that in the case of spin of the secondary spin, the bias is greater, but we think that this might because we are drawing samples in the whole range of spins, and normally BNS and NSVH events have narrower secondary spins. So, but we are still studying these results. So the summary is that we have developed this method that is able to estimate uncertainties in component masses and spins in less than a minute. And what we think it could be used to is to improve the source classification that we make while computing Piastro, because we now have a better estimation of the posterior of masses. And then also that this set of samples can be used for a following and more exact calculation of the likelihood. So one of the advantages of these pre-calculated samples is that they are not correlated between them, as it happens with Monte Carlo generated samples, and well, they are close to the true value of the event. So yeah, they could be used to recalculate the posteriors with a real likelihood computation. And if you have any questions about this, I will be very glad to answer them. Thank you.
Thank you, Verónica. Very, very nice talk. We have questions. Okay, then as people gather their thoughts, I wanted to ask a clarification about the mismatch. There was a scatter plot.
Yes.
Early on.
This one. Maybe? Yes. Okay.
So isn't this the mismatch defined like between 0 and 1?
It doesn't have to be between 0 and 1, I think.
So it's not 1 minus the overlap?
Is 1 minus the match, but I think the overlap and the match are not exactly the same.
Right. I guess that was. All right, I'll have to look this up. I was surprised by the values. And then the other question I had was, so you're focusing on intrinsic parameters, not on time maps. Okay,
that's true. For the moment, we have been thinking to work a bit on extrinsic parameters, but we are not getting to that at the point.
And then there was the manifold figure you showed. So are you using
here?
Yes. Are you using post-Newtonian parameters like this is technically, or principal components that are combinations of parameters?
We are using post-Newtonian parameters.
Okay.
We are,
Yeah, because I think this figure refers to like linear combinations of
maybe. Yes. I took the image from Frank's paper, because I think it gives an idea of the flatness of the waveform surface in a bigger parameter space. But it's true. I think Frank uses principal components.
Okay, do we have hands up by now? All right, I don't see any hands up or questions in the chat, so I'll thank you once more, Verónica, for the nice.
Thank you.
And last but not least, we have Malachi Bloom coming on, yes, who is presenting angular resolution of the search for anisotropic stochastic gravitational wave backgrounds with LISA.
So I'll be talking about the angular resolution for the search of anisotropic stochastic gravitational wave backgrounds with LISA. My name is Malachi Bloom. I'm going into my last year of undergrad at Carleton College. So if you're shopping for graduate students this upcoming year, my email's at the bottom. Anyway, I'm basically going to go through this talk backwards through my title. So I'll say a few words about LISA. Then I'm talk a little bit about stochastic gravitational wave backgrounds. Then I'm going to add the word anisotropic onto that and discuss why that's important and think a little bit about how to deal with that. And finally, I'll go into sort of characterizing the angular resolution of these anisotropic surges. So what is LISA? Well, LISA is a space-based gravitational wave detector. It's going to be in the millihertz frequency band, which is lower than LIGO. Set to launch in the 2030s. And the thing that we care about in this talk is that it's very likely going to detect stochastic gravitational wave backgrounds. Okay, so what are stochastic gravitational wave backgrounds? Earlier in this session, we heard a talk from Robert on cosmological backgrounds with LISA. And so these could be from a whole range of things, from cosmic strings, early universe phase transitions, primordial black holes, inflationary models, and probably a bunch of other things. I don't know anything about those, but I'm told that those things are relevant. The other side, the other sort of class of stochastic gravitational wave backgrounds are the astrophysical things, and those are sort of things that are happening today from astrophysical events. So some important examples are white dwarf binaries in the Milky Way and in the LMC. And in fact, there's going to be we think that there's going to be so many in the Milky Way that it's been promoted from the level of background to foreground. So individually, we can't pick out these double white dwarf systems, but because there's so many, they culminate into this sort of foreground or background that we can hear in the detector. There's also stellar origin binary black holes, which I believe are supposed to produce a background, and probably many, many other things that you could imagine that could conceivably create a background in the LISA band. So how should we go about thinking about these things? Well, a group at the University of Minnesota and elsewhere has developed the Bayesian LISA inference package, or BLIP. And BLIP essentially can do two things. It can simulate stochastic gravitational wave data, and it can analyze that data. So it simulates data as if it were real data in a time series with frequency information, spatial information, and also taking into account different models for the instrumental noise associated with the LISA detector. And then it goes about analyzing this with the simultaneous Bayesian inference, hence the B in BLIP, and it's able to recover that data, the spectral, spatial, and noise distributions independently of each other. And it can also take into account different models and eventually simultaneously infer different stochastic gravitational wave backgrounds. If you want to know more about BLIP, there's a paper from Sharon Banerjee, and also you can check out the GitHub, which I've put on there. And also, if you want to hear more about this, Alexander Criswell had a talk on Tuesday about this very package. It's the it's 06A1. So eventually, I think the recording should be up and you should be able to find that. So BLIP is really important. One way to sort of view this talk is an extension or working off of this BLIP tool and sort of seeing how well it can model and recover these anisotropic surges. So just to give a little bit more insight into the stochastic gravitational wave backgrounds that are sort of motivating this are the astrophysical side of things. So on the left here is a plot that you may have seen before, and we can see that the Milky Way foreground is in the gray there in the bottom left. And on the right, we have the LMC stochastic gravitational wave background, and you can see that it's a little bit lower. But those are two examples of astrophysical stochastic gravitational wave backgrounds. Now, the important thing that I want to point out about these sources is that they are anisotropic, which means that I personally can point at them. So There's spatial information that we can use to sort of attach to these stochastic gravitational wave backgrounds. So if you're interested in finding these specific backgrounds, maybe you're interested in them just for the astrophysical data, or maybe you want to remove these signals from your stochastic gravitational wave background to look for more cosmological backgrounds. Whatever your reason may be, you can sort of use this spatial distribution most likely to do that kind of thing. If you want to know more about the LMC side of things specifically, Stephen Reich has a paper in preparation that's all about using blip to think about and model the LMC stochastic gravitational wave background. And he also has a poster at the Amaldi Conference here, which is number 219. So as I mentioned, these are anisotropic signals. So if you choose a specific frequency, what you can do is map the gravitational wave energy density across a sky map. And you get something that might look like this. And this is a nice way to sort of visualize the spatial information associated with the stochastic gravitational wave background. So the Milky Way foreground would look like something there on the left. If there's a paper by Alexander Criswell in preparation that's going to be thinking about using blip and all about the Milky Way foreground. And as I mentioned on the last slide, Stephen Reich is working on a paper with the LMC. One thing to note with these sky maps is that we're plotting the gravitational wave energy density, and so it ranges from like 0 to some like positive number. In contrast to something like the CMB, where you have some constant and like fluctuations up and down from that constant. And this is going to be important when we think about analyzing the distribution of this energy with spherical harmonics. So just keep that in the back of your mind for like just a second. Okay, so eventually what we want to be doing here is simulating a point source stochastic gravitational wave background and going about some analyses. So we need a model for that. So we start off with a power law for the gravitational wave dimensionless energy density there at the top. And it's just a straightforward power law with frequency, and this omega naught essentially just kind of shifts it up and down and tells us how loud the source is. So now we want to make it anisotropic since we're thinking about spatial distributions, and to that we can just simply write this function over a sum of spherical harmonics. But as I mentioned on the last slide, we need to make sure that the gravitational wave energy density is non-negative, because doesn't make sense to talk about negative gravitational wave energy density. So to do this, we do a Clebsch-Gordan decomposition and essentially rewrite these ALMs in terms of BLMs. And so as long as these BLMs are real valued, you can be assured that this omega is going to be non-negative, which is exactly what we want. If you want to see more of the details on this, you can, again, check out Sharon's paper on blip. The important part for us today is that all of the analyses with blip are done in these BLMs. And so when I report the results, they're going to be in ALMs because that's more familiar and that's what we usually think about, but they're going to be in even numbered, and that's because the map between the Lmax for A and the Lmax for B is given by this. So the maximum L is half that of the maximum A. So keep that in mind when you're looking at the results. Okay, so with blip, what can we do? So essentially we can set, we're going to simulate a point source in the sky. We're going to give it some parameters. It's going to go through, simulate that source along with some noise. And then we can take the data that it spits out and select more parameters and analyze that signal. And then eventually we'll want to characterize this angular resolution. So some of the parameters that we're thinking about are where in the sky it is, that omega naught from this model that I discussed earlier, the duration of the orbit around behind the Earth, and the final one that we're looking at for these single point injections are the recovery Lmax. And that's when you do the analysis, you're writing that model over spherical harmonics, and the Lmax tells you like what resolution are you using to conduct your analysis. Okay, so now the question here is, how do we characterize angular resolution? So inspired by EM astronomy, we found that using a full width half max is a good way to go about this. So what we do is we take the sky maps that we get from the blip analysis, and we look for the maximum point on the sky that has maximum gravitational wave energy density on the sky over the spherical harmonic basis. And then we look for all the points on the sky that have above half that maximum value, draw a red circle around it, and then the fraction of the sky that's contained within that red circle is going to be like our metric for characterizing angular resolution. So as the fraction of the sky goes down, we get better and better angular resolution. And so these plots on the bottom are showing you different analyses for changing the Lmax that we're choosing to recover the signal at. So you have an Lmax of 4, 8, 16, and as you increase the Lmax, we're seeing a tighter and tighter full width half max. So we can plot this. Here we have that spot size, that fraction of the map contained in the full width half max versus the AL max. And I've also plotted different choices of the omega naught, which are just basically different strengths of the signal. So from here, what we can see, perhaps unsurprisingly, is that as you increase Lmax, the resolution that you're using to analyze that sky map after blip spits or in the blip analysis, as you increase that, we're getting tighter and tighter or smaller spot sizes in the sky. And we can also see that there doesn't seem to be much variance in how loud the signal is. All of these error bars are overlapping with each other. And so from this plot, we see that a really dominant factor here is the Lmax that you choose to recover at. This is really nice because Lmax is a computational limit. It's something that we choose. It doesn't come from something physical in the system. It's simply something we get to choose. You may ask, well, why didn't I go out to Lmax of 100? And the answer to that is because it's very computationally expensive. I think these data points at Lmax of 16 took on the order of 16 or 20 days. But this is exciting news because as work is continuing with blip and making it faster and faster, we're going to be able to push these limits even more. And I guess the other thing to note here is that we don't seem to have hit the detector's limit yet. The limit is with the analysis. Here's another plot. On the x-axis, we have different strengths of omega naught, and then I've also plotted the orbit duration. And here we're not seeing huge significant factors. The one thing I should note is that if you look at this, it doesn't seem like changing the strength of the signal has much of an impact on the angular resolution. But if you go to the left of this plot a little bit, so you decrease the strength even more, you don't recover at all. So when it comes to the strength of the signal, you either recover it or don't. And once you do recover it, increasing it much more doesn't seem to have a huge effect. Okay, so the other thing that we can do is 2-point source injections, and it's basically the same exact song and dance before, except now we just add another point in the sky. And the other thing that we can think about is changing the distance between these 2 points. So now we want to ask, how do you characterize this angular resolution? So we come up with a metric, which is take the distance between the 2 blobs that you have in the sky, this D here, and then the area of these blobs, the full width half maxes, and do the distance over the area. And so the key point to notice here is that as the metric increases, your angular resolution is increasing as opposed to the last metric. So here are different signals of taking 2 point sources in the sky and moving them closer and closer, and eventually they become one blob that you aren't able to recover. And so here's a quick result. On the x-axis, we have the angular separation of the injected point sources. So pi, 0.8 pi, 0.6 pi, 4, etc. And so as you see, as we bring them closer to each other, you reach a point where we can't resolve those signals. There's still a lot of ongoing work on this with choosing different Lmaxes and exploring different omega knots. These are my acknowledgements to MSI and my mentors, and I'll flash the conclusions as we go into questions. Thank you.
Thank you for the talk. Do we have hands up for questions? Okay, I don't see hands up. I will ask, I guess, a generic question. So what are the steps forward? I mean, you characterized this in terms of one point injection or two. What comes next?
So the big goal for us is understanding the point spread of these of the blip tool, because what we have in the back of our minds are these plots with the Milky Way and the LMC, and we have a spatial distribution of these sources. But the question is, well, what are these spatial distributions coming from? Is it coming from actually something physical in the galaxy, or is it coming from some relic of the detector or our analysis tools? And so if we want to understand the signal as best as we can, we want to sort of figure out where these distributions are coming from. So doing more thorough analyses with more sophisticated injections is sort of the next step, I would say.
Perfect, thank you. Any other questions for our speaker? Okay. If not, I'll thank you once more, Malachi. It was a very good talk. And since we're ahead of schedule, I'll thank once more all 7 speakers we had today in this session. Thanks for joining, and I'll hand over to Scott.
Yeah, and just to thank you very much, Francesco, for chairing and for asking questions and keeping us all organized. So thank you very much. The next sessions will start, I think, in about 6 hours again, so 6.5 hours. So take care, everyone, and thanks.